as I was saying, so I'd like to introduce Martin Raum, who's from the Max Planck Institute, is a student of Don Zagier. I'll be talking about the situation regarding modular forms in Sage. Thank you.
Yeah, thank you. I mean, actually, this won't be a research talk like the preceding one. It's rather kind of an advertisement for a certain framework and also overview what we have so far achieved, not only in particular with one-dimensional modular forms, say elliptic modular forms that are until now mainly the focus of our work, but rather with things like Siegel modular forms that are, at the moment, they are kind of a hot topic in the sense that we would like to really test certain conjectures. We have vector-valued Siegel modular forms that promise to be very, very interesting objects, but it's hard to handle them even in, say, vector-valued case 2 or so, vector-valued weight 2 and so. And actually, the goal of this whole project that I'm mostly working on this with Niels Dorper and with the guys in Aachen, that's mainly PhD students by Cree, and also Nathan Ryan is involved in that. And we are kind of trying to improve the situation with regard to this, and also what concerns me with respect to Hilbert modular forms, Hermitian modular forms, and so on. So first let's see what has been the past. Certainly Sage is famous for having good support. We had it very initially. That's probably also due to William, who that's just one dedication of the project. That had been at some times surprisingly slow, and we fixed this just this week. I mean, certain things with decompositions and so on, well, at least I started to do more deep work in this code to try to fix certain speed issues, and it's certainly not the last thing that we will do. I mean, we will get eventually equally fast to, say, Magma, which at that moment is in most cases it's faster, but we do already have some things where we are faster. That's certainly a task that is on my list to finally beat Magma. And most users wanted that for elliptic curves and so on. That was certainly one of the main applications. And that means, that's really striking to me. That's why I'm mentioning multiplication of modular forms wasn't implemented for a very long time, though it's very trivial. You take the power series, you multiply them, and you re-recognize them. So mainly people were thinking from one point of application, and then they were missing this crucial thing that other students, for example in Aachen, were really missing when I was demonstrating Sage, and they were wondering what happens when I multiply two Eisenstein series, because you can, of course, check due to the products of Eisenstein series of two Eisenstein series spans the spaces. Of course they do, that's a theorem, but students do want to see that, and I couldn't make them see. So now we've got this. That's very good. But actually this situation is only like that for integral waveforms. For half-integral waveforms, we do have Magma, which I think for everybody who is concerned with half-integral waveforms will mostly use Magma because it's really easy. And we do have an implementation, I think William provided that, for half-integral waveforms, but it's really nasty to use, and it's slower, so nobody will use that probably, and also half-integral waveform, which is of course a corner case, and it's more difficult, but we don't have it, and Magma does. So that's certainly one of those things that we should probably next do with modular forms. Until now we are mainly focusing on integral weight, and half-integral weight obviously is neglected. So what more? I mean, I have mentioned Hilbert modular forms. That's also what I'm aiming at, not so much as orthogonal modular forms. I mean, orthogonal modular forms for n equals or greater equals 3. But Hilbert modular forms form a special case of orthogonal modular forms, so they are in my area. And it's interesting, Magma does have an implementation. Demle was writing all the details of this Langlands correspondence. And Voigt essentially used this with the help of Demle to provide an implementation in Magma. And we've got, I just was talking yesterday to William, we've got an implementation actually in heap space. Until yesterday I wasn't aware of that. And it seems to be the fastest ever. I mean, he obviously put a lot of work into that, and nobody will beat in that special case, but apart from that, of course, we are still missing a lot. I mean, most people will not first take square root 5, or, well, they want to do more, though that's certainly also one of those things that could have been done. And then, very recently, support for imaginary quadratic fields has been provided, but the bad point is that it's not in Sage, but it's in Magma. So we would like to have something like that also. I mean, Bianchi modular forms, that's, for me, when I'm teaching, it's really nice to have, because there are some very non-trivial statements that you can prove with Bianchi's original papers, and if you have those modular forms on the computer, you can make students easier believe that certain fundamental domains are nice. So for teaching, it's certainly nice, and for research, that, as far as it concerns me, I'm not so much interested in that, but of course, I mean, it does have applications. So, yeah.
You're welcome to have my C++ code for the last part.
For the imaginary?
Yeah.
And Rapid?
Yeah.
That would be nice. I mean,
Better than nothing.
yeah, certainly. I mean, if you've written that, I suppose it's good. Then.
Well, in my talk on Monday, I said the first version didn't work. that was in 1979, so yeah.
And then, of course, SAP sharplies are the way to go in modern research with those forms. I'm not sure, probably you didn't.
No, I didn't use those.
Yeah.
I use modular symbols.
Yeah. So that they apply for other things like Jacobi forms, and Niels was actually talking about using them to provide an implementation of Jacobi forms. That was kind of 2 years ago, and just recently, 3-4 months ago, I was talking to him. I was needing this for some other projects, and he probably won't do that. So that thing is open, and probably everybody who wants to pick up this tasks. The theory is not easy, but I mean, it's feasible, it's worked out, and so it could be done. Let's see what our strong sides are. I mean, until now, mainly, it seems like Magma has a slight advantage, at least to me. I mean, Hilbert modular forms, also things, we still have a lot of work to do. But our strong sides are there, and that, for example, Siegel modular forms. That is track ticket 8701. So it's lingering around for a kind of a long time. We are now with 11,000. I recently opened 11,017, which shows us that there has been some work done, but we are still not really have still not completed the task. And what we want to do is actually to provide an implementation of Siegel modular forms with hacker operators, preferably also vector valid, but at the moment the code reliably only works for a scalar valid form. There have been some issues with vector valid form, and also that's a speed issue. I mean, scalar valid modular forms are fast. I've used them, or rather I've used an adapted version which was even faster, but vector valid forms are not really optimized. That's mainly because multiplication is not coded in Python, but in Python. And that's, of course, I mean, it's kind of a trivial task to do it, but it's a nasty task. So, and this has been done by several people, including me. But the implementation, it was started by Skorupa, and Nathan also joined in that project very, very early. So, and yeah, as I said, we would like to have vector valid modular forms, because that's really, if you consider hardest conjecture, for example, it really shows us that that's the way to go if you want to understand better what is going on there. And actually, talking about, just going back one slide, talking about vector valid modular forms, one probably should mention the work of Gerhard van der Geer and Jonas Bergström. They are taking a completely different approach. By computing hacker eigenvalues only. We are actually handling Fourier expansion. They only compute hacker eigenvalues, but they, as a reward, they can really compute high vector valued weights. That's absolutely out of reach for our approach. So we can probably do, we certainly can do weight 2, weight 4 should be possible, weight 6 might be slow, and so on. We are, well, for 4 we do have generators, for 6 I'm not aware any work on that could be. One could try, of course, to use the dimension formulas and see how far one gets. That's certainly possible. And there is no view of Charlie's. I mean, the work of Jonas and Gert, that's certainly a good big contribution, but it's not as a complete theory as we do have with modular symbols or Charlie's. So we cannot expect this approach, whatever approach we take, it cannot work for any congruent subgroup at the moment. I mean, we just have to fix special groups like the full modular group, which is certainly the easiest, and then do work there. And that's of course sad, but it's not so much of a pain because there are many unsolved problems already in that case. So having computations available for that situation would already be good. And actually, there have been computations done. So strategies for this implementation, as I pointed out, there is no modular symbol theory, so that takes a rather naive approach, just provide as many constructions as we know. And we know that, for example, we can span spaces by theta theories or invariant of theta theories, which is of course ridiculously slow, but in principle we can't of course have every space in terms of generators, and so we could try to implement good generators and then span the space, and that's actually what we do. Mass lifts are the most promising thing, also because they allow for computations with very, very high degree. I did some very, very expensive calculations, say, for Siegel modular forms where I needed mass lifts, and I got up to weight 170, which is good, I think, and I could compute spina L series with eigenvalues for 1,500, primes up to 1,500. And that's certainly something which is only possible with such structured constructions like mass lifts, and that's even if we had modular symbols, that would be out of reach with this approach. In that case, we really need mass lifts. Theta theories and Borchardt products are certainly those constructions interesting for all of us who are involved with orthogonal modular forms, which in this room might only be me, but well, it is a very nice approach if you're, for example, interested in Kac-Moody reality class and so on. So that's certainly one thing people are also interested in. And for vector-valued modular forms, very important are Sartor brackets, which are just a special case of Rankin-Cohen bracket, but Sartor brackets we call them because we can span vector-valued weights too with those brackets, and that's very interesting and that's very, very useful. And what we've got to say about this approach, it's a systematic approach in the sense that we know that we will get every Siegel modular form of a certain group. In contrary to what mainly Pur and Yen did when they were computing spaces for degree 4 forms, for example, that's really amazing work. Or, well, they were doing different approaches for that degree 4 case. So they have proposed several things that are really, really interesting, and I will come back to this later because it might give a substitute for not really, it's kind of a synthesis between Fourier expansions and modular symbols that you can build up from their approach and our approach, and that would be perhaps even a perspective, but there are not even there is no implementation of that. That's the plain idea at the moment. An example, just to say that we really can make this concrete, that is a very classical theorem. That's a space of Siegel modular forms that's spanned by 4 forms as an algebra, and that's all mass lifts. The egos are lifts, and it's, yeah, I mean, and that makes them really, really easy to compute up to very, very high precision. That's not so difficult. It's more difficult to compute the 6 generators. For this ring of vector valued weights too, that's 6 generators in terms of Sartor bracket, and there we have to differentiate and so on. That can be made fast, but then it involves multiplication, and there we really got a problem. We cannot go up to so high precision as with mass lifts, where we easily can say use discriminants of 1 million or so. not really easily, but it's perfectly feasible, and it's not with multiplication, that's definite. At the moment, not. I will also come back to this problem later, but let me say, Siegel modular forms should really be there. We had 2 deadlines already, which we've all not really kept. But at the moment, Nathan, Niels, and Gonzalo are at the MSRI, and we really want to do that. Actually, we already wanted to have finished that project. We are still on this task, so, but let's hope. I mean, MSRI, they are still until May, so they have time, and I will also work on that. Might be that we will have in May a really good implementation of Siegel modular forms in Sage. There are, of course, more modular forms, and now it comes to orthogonal modular forms, certainly, but the approach is very, very general, so everybody who's interested in Siegel modular forms of genus 4, there is a stub implementation of this also. So let's see. I mean, there are, of course, genus 2, which is very complicated. Jacobi forms of lattice indices, they mainly play a role for orthogonal modular forms, but they can be interesting on their own, certainly. Paramodular forms are very, very interesting, and there is only one implementation of this, I think, that's due to me, and it's not so well known, but you can find it on my homepage, and I did some calculations with that. It works nicely. I mean, I haven't done too much work on that. And then, of course, orthogonal modular forms, where most people know Hermitian modular forms, few know Quaternion modular forms, and 025 is very, very badly known. I mean, it's kind of a restricted Quaternion modular forms, but it's really a nice object because Hermitian modular forms we can deal with up to a certain extent. Quaternion modular forms we are actually in the process of determining the graded ring for the Quaternion algebra ramified over square root over 3. But, and we know the one ramified over 2. But apart from that, we know almost nothing about Quaternion modular forms. And 2.5, we know some graded rings, we know some structure, we know some Bartels products, and so on. There are exceptional constructions for 0 to 10 even by Freitag, but that's very, very vague. And at the moment, we would rather focus on those 3 cases where we really realistically compute anything. Well, the applications is mainly to get some results for Siegel modular forms, for example, by restricting Fourier expansions. That's one thing I'm very interested in that. But of course, Hermitian modular forms, by being just having Bartels products associated to, would be interesting for Kac-Moody algebras again. So that's just this application again. So let's turn to this framework, and I will not so much talk about modular forms because I am aware that most people are not so interested on orthogonal modular forms in this audience, but they are interested in Fourier expansion because every modular forms, well, except some cases we cannot deal with, like U13 or so, but most modular forms that we really want to compute with do have a Fourier expansion, so a Fourier expansion would be nice to efficiently deal with, and that's actually provided by this framework that is not yet in Sage, nor in neither in P-Sage, but I hope to do that kind of soon. I actually, one of the reasons why I came here was to get some feedback on that and how people think about this thing. And more realistically, of course, it will get into P-Sage because it's a bunch of code that nobody wants to review. I mean, even the core of the framework is 12,000 lines that is fully doc tested and so on, so that's okay. But the rest is not doc tested, so that's even harder to get in Sage. I mean, no chance. Almost all types of the modular forms that I have mentioned are implemented. In particular, Siegel modular forms of arbitrary genus are in principle available, but they are double doc slow. I mean, that's not really usable. I did some stub computation with that, and it's usable, it runs, but you have to be very, very patient. And the outcome is not really telling you much. I mean, there are some people even who don't expect to see Siegel modular forms of genus 4 in a greater amount in the next few years, and probably they are right. I mean, we have to focus on different things. And the implementation, that's just because I'm interested in that, is focusing on L series. It attached to those single modular forms or orthogonal modular forms, and it's optimized for that. But it's also good for investigating the structure, like the generalization of this Eisenstein product thing, that you can span spaces by products of mass lift, for example. That's a conjecture until now, but it's a very, very important conjecture what concerns computations because it makes computations feasible. You do have very, very easy objects and you just need to multiply 2 of them, and that's much easier than multiplying Giza generators or whatever. And that's actually feasible with that framework, and Sturmbounds I investigated a bit joined with David and Chris, and congruences I investigated not by me but by Olaf Richter, mostly. Yeah. So what I want to tell you is how easy it is to implement those Fourier expansion, and that's mainly why I've written that piece of code, because I wanted people to be able to provide Siegel model forms and whatever they have in as easy as possible way, because we will not only need to implement Siegel model forms, but many, many other forms. So we want to have as a monoid of Fourier indices that's typically square, integral, or even matrices, and T, a group acting on the Fourier expansion that's normally a TLN for Siegel model forms, TLN of Z, that just comes from the Levy component. And with that, we normally do have all intrinsic symmetry. All other symmetry is normally hidden, so we cannot model that. But we should model that symmetry because it saves a lot of memory, and without that optimization or without exploiting the symmetry or storing Siegel model forms is completely out of reach. I mean, it's consuming too much memory. And then, of course, yeah?
For classical modular forms, so S would be the positive integers or non-negative integers? And then
For elliptic, you mean?
Yeah.
Yeah,
and
that's
then what's G?
It's a trivial group with one element, because
All right.
we only have translation there. But that's exceptional, and even for Hilbert modular forms, we already have more symmetries that we really need to exploit. And then we do have precisions. Of course, everybody needs precisions. Nobody will store Siegel modular forms up to infinite precision, and that's just C finite subset in the sense that the complement should be T invariant, and it is the union of finitely many T orbits. That's just because we only within one orbit we only need to store one coefficient, and finitely many because the computer can't do better. And then in algebra, or rather in R module, we really need R modules here. Normally we do have something like Q bar or whatever. But for Siegel modular forms, of course, we want to have vector valued forms. Or in general, we want to have all kinds of modular forms that arise from the decomposition of the Hodge bundle. And there we will have modules, only and not algebra, and that, for example, normally symmetric polynomials with coefficients in Q of homogeneous degree 2, for example, for vector valued weight 2 for Siegel modular forms. That's one typical example, and normally we will also have characters, and in that case, because we will multiply different characters, we just model that by a homomorphism from a monoid, whatever structure it carries, to the homomorphisms to say Q bar, because we normally will only treat rational modular forms. And then, that's the point, we need only to provide very, very few things. That's first the T action. We cannot expect to come out to finish this without the T action on the indices, which normally means that we have to provide a representative of each index. That's, for example, that's Gaussian normal form for binary quadratic forms, if we consider Siegel modular forms of degree 2. And the character, that's just evaluation of the group of this character on this group, or actually the representation saves very much effort by passing to certain representatives of that group that we only need. So implementation can really specialize on only those information that it needs, for example, if we have the full Siegel modular group without character, then we don't need to pass around those group elements. That's really convenient and it saves a lot of time. And then the filters, of course, that's just in enumeration of the representatives in S. And for multiplication, we need the decomposition of S, which is, as you probably guessed, a very naive approach. I mean, we don't have any very fast multiplication for this kind of Fourier expansion. And this is just a set of S1, S2, that which product equals S, which is given. And that's just for computing the multiplication. And at that point, we can even provide a more specific implementation in Python, typically, that makes this multiplication really fast. And that I normally use for all real-life applications. I mean, the other thing is only for convenience if you really have to program just a start to see what whether things are going well or not. And some helper functions, but those are tiny. It's really not so much like give me the group name of the group that I'm dealing with and so on. And from that already the framework makes a Fourier expansion, and that's really amazing, I think, because it saves a lot of time for everyone having this thing at your hand. And for just illustration, I want to have this example, a symmetric algebraic power series. That's kind of true. We all know that's, that's implemented in Sage. We don't, but it does have symmetry in that case, and I will implement it as just monomials that are saved in Y representatives with respect to the symmetric group, and that's just a very, very easy example. So reduction of elements of S can be just performed by sorting those indices with, if we have a tuple which gives us the exponents of such a monomial in that case, then we just can sort it and we've got a representative. And the second thing is just the return statement just returns the elements in the sorted group without this helping parameter which we needed to get the permutation. You see, I'm sorting the thing, but I'm saving the permutation at the same time. That's just the trick. The decomposition, of course, is also very easy. I just iterate over all those subtractions. I iterate up to the tuple S, and then I subtract. That's very, very easy. You see, it's really easy normally to provide those functions, even if they have to be fast. That's up to now we have, say, 6 lines of code. That's not much, and we are half done. The filter, we need to check whether elements are contained in a filter, but that just means that either a bound B is infinite or an entry of S, the index for the monomial, is lower than B, the bound, and that we do for all exponents, and we are done. That's 2 lines. And we need to iterate over reduced elements. In that particular case, that's very, very easy. In the case of Siegel modular forms, that's more code, because we really have to translate all reduced forms, but in that case, it just means that we use all increasing tuples of n, which do not exceed a certain bound. That's the self-dot-bound. And the implementation, the framework already provides trivial characters and trivial representations, which means that we don't have to do anything here, because we only want to have symmetric algebraic power series. But if we liked to, we could, for example, use character. Then this would give twisted symmetric algebraic power series, which of course is as pointless as having symmetric power level theories implemented, but it's very useful for Siegel modular forms, for example. And then this is all you need to actually provide the implementation. All what I've shown so far goes into this first line n monoid, and its associated filters that do not show up. They are referenced to within that first class, and then the trivial character and the trivial representation is already given. in the framework, and A is our base or coefficient ring, and that's all. Now we've got actually ring of symmetric algebraic power series, and that I think very useful, because if you've got single modular forms, the lines of code that you have to write is not much more. And the main work that you have to do is really in this first monad. And there you can focus on the really important task where you really need to gain speed. Then just some words about these generators. Often massless gives a set of generators, at least in the orthogonal setting, we know that. Sometimes we have to add Borchardt products, which is bad, at least from a computational point of view, but it's really realistic to normally work with massless. And in principle, the theta series are sufficient, as I mentioned, but of course that's really slow. Nobody wants to take that. But yeah, any reasonable implementation will provide that, and actually Nathan, Niels and me and Gonzalo also, we have the theta series. That's very important, I think, for application. And Borchardt products are not really implemented, except Nathan, he was thinking about providing a very naive implementation, but that will be slow. I mean, we all know that Borchardt products are not easy to evaluate, but we do have a new algorithm, and I'm working on that with people in Aachen, and we hope to be done next autumn or so, and then of course it already is in Sage, so as soon as it's done it probably will be in Sage or so, so that would be better. Very, very important, I think, for applications. So there's only one thing I have, for one slide I have to say about the future, because it's always harder to talk about the future than about the present. And of course the first thing is get the thing into P-Sage, that's mainly due to me, but then use it, that I can only do for a limited extent, that's mainly due to you, to actually find out how useful that thing can be. And then very, very disturbing is that we have to use naive multiplication. We cannot use Fourier transforms for multiplication just because this blows up memory. We would have to we would have to expand Fourier expansion, not using symmetry, and that leads to multiplication by 10 to the 10 or whatever, depending on how far you get of the space. I mean, when I computed up to the experiment of 1 million, I was consuming something like 10 gigabyte of memory, and without the symmetry of that wouldn't have been, I mean, not with 400 gigabyte, I couldn't have done that. So we need really a new approach to multiplication for equivariant power series. That would be very, very useful. I'm thinking about that, but well, until now, the results are not so usable. And then, of course, I mentioned this modular symbol thing, that's a Fourier expansion. It is really a naive approach that we've taken, Niels, Gonzalo, Nathan, and me. But it's at that moment it's the only feasible one. Very recently, I've proved conjecture by Pur and Yen, which means that we can have formal Fourier Jacobi expansions, which essentially reduces us to computing Jacobi forms. That was actually the question for Niels, why I really needed Jacobi forms, because I wanted to implement this approach. Well, we don't have Jacobi forms, we won't have them in the near future, but if we have them, then the problem of determining the Fourier expansion of arbitrary single modular forms really is only linear dependence between formal expansion of Fourier Jacobi forms. And already Chris and David have used that. In mathematics, they normally program, so we would have to. It's surprising, isn't it? They do good things. I mean, it's really surprising. They must be good if they can even do something like that with mathematics. But well, I could port that certainly in a joint effort. They are currently very, very busy, I think. Yeah, they are. But in a joint effort, that would be not too hard to port that code. Now that the conjecture is proven, that would be very, very useful, I think. And then, of course, questions. I would like to have questions from you.
Did you say you proved Poor and Ewan's conjecture?
Yeah.
What is their conjecture?
That every formal Fourier Jacobi expansion is actually, if it has the switching symmetry, which is induced by the, say, J matrix within the GL2 component of the Levy decomposition, of the Levy factor, then this is already the Fourier expansion of the Siegel modular forms. Which, of course, makes it very, very easy to compute those Fourier expansions. It's much easier.
And is there a way to find the corresponding Siegel modular form?
Well, what does this mean? I mean, having a motive and then finding the Fourier expansion, that cannot be done. I mean, you can normally check the eigenvalues and check, for example, with Calabi-Raum manifolds. And we had this issue 2 years ago in Benasque in this workshop. We had a... But then we weren't able to do that. Actually, we would have needed to compute too many Fourier coefficients. But at that time, of course, the framework was in this very beginning. I mean, that was actually the case when I started this framework. Today, we might be able to do that. I mean,
what sort of thing goes into the proof?
Sorry?
What sort of technique goes into the proof? What's the idea of the proof?
We use rational points of the upper half plane. And we use local convergence around all of those points. And then we use finitely generating of the ring of weak Jacobi forms in the sense of Don and Eichler, which means that if you allow for only positive indices n, but for r you don't have any real restriction, then you can have the ring generated by 3 elements. And with that, you can easily deduce from this local convergence, for this convergence on rational point, that it is really a Siegel modular form. Actually, convergence is the only issue there. And that, of course, I mean, it works for all orthogonal modular forms. It works for very, very, whenever you have a kind of partial Fourier expansion, where the ring of objects that the coefficients form part of is finitely generated, and so you have something like a rational points which are dense, which normally for all kinds of modular forms we have. I mean, I'm not computing with stacks or so. Then actually the proof works, and that's actually how it's formulated.
Nice. Cool. So any other questions or comments? Let's thank Martin again.